Hey, so I wanted to show you how to solve the problem in this video, and this is a problem thought to be solved using more advanced theory. This is a problem about something that is called permutations and combinations, which you don't know yet, but this one is, I thought, a fun way to introduce the next topic, and it's also solvable because you just have four different objects. So the universe of the possible games, of all the possible plays in this game, uh, it's really small, so you can actually write down all the possibilities and just analyze it from there. Kind of make a table and count the possibilities for each of the questions. So the specifics of the game, it says that we have four positions, so we have just, let's say, four slots, and we also have four different color packs, and we are two players are have the same board, have the same color packs, and they are putting them in different orders. And the second player is trying to guess the configuration of the packs as placed by the first player. All of these packs are of different colors, so that makes these objects perfectly distinguishable from each other. So you have at all times four different objects in four different positions. Okay, so these are the full, this is the full list. This is a table with all the possible combinations for the game. If we actually name, I'm not using colors because it's just the same, it's just a way to distinguish the packs, but I'm calling them A, B, C, D. So if you call the packs A, B, C, D, these are all the possible combinations that you can have, starting from A, B, C, D, and then the different combinations that you can make. Only 24. You cannot have more than this. And if you pause for a second and actually try to work it, like count these ones, or try to make it by your own, you'll realize that these are actually all the combinations that you can form. Now, let's say that the player one has actually formed a sequence A, B, C, D. We can actually do that because we don't know what player one is doing, but it's all the same. It doesn't matter because all combinations are equally valid. He could have chosen another one, but it's just the same, or we could have relabeled all the packs to make them just A, B, C, D. So it's all the same. It's pretty general. And now for the questions. Question number one, well, question A. What is the probability that the second player has all four packs correct on the first guess? And this means that the player number two would need to actually choose the same configuration as player number one. So there is only one option that the second player can choose to make all four correct among the full universe of options. So the probability is 1, which is the successful one, over 24, which is the full universe that we're talking about. Probability for this is 1 over 24. Now for the second problem, you have this question. What is the probability that the second player has exactly one pack correct on the first guess? And again, this is just about two turns. Player 1 chooses the arrangement, player 2 tries to guess, and that's it. This is that's the end for this question, because it's only about on the guessing one pack correctly on the first try. For the sake of the argument, let's assume that the um, the pack that it's going to be correct is the first one, it's A. So the player number 2 has to choose some options, some arrangements in which the A shows first. These are all included, the correct one. These are all the possible arrangements of the packs that the player 2 can choose from. So A comes first. but it says that exactly one peg has to be correct. So only A has to be correct. We have to take out all the possibilities that have more than one peg correct, and that means that we have to take out the B. All the possibilities that have B also correct have to go. That means this one. Then all the possibilities that have C on this one have to go. That means that one. And then all the possibilities that have D on the last column have to also go. So there it is. And of course, this one is also a possibility that the second player could have chosen, but it's not a good one because that would have all pegs, all four pegs correct. So for the second player, these are the only two options that she has to actually um, make correct this question, that on the first try only one of the pegs is correct. And that is us analyzing the case in which the first peg is the peg that is correctly guessed by the second player. But we can repeat this with B or C or D, with the peg on the second place or third place or fourth place. So we have two possibilities as well for each one of these, because this analysis is completely general. And then that means that the probability is just the two that we can have for any of the pegs that we're saying the second player has correct over the full universe, which is still 24 options. So the probability is 2 times 4 over 24. That's 8 over 24, and that's 1/3. So it's a pretty good chance that on the first try, on the first guess, the player 2 has one peg correctly positioned on his board. And third and final question, the second player is told that she has placed two pegs in the correct slot. The player then switches two of the pegs. What is the probability that the player now has all four pegs in the correct slot? This one is a tricky question because we have to distinguish that this one is a question about what happens on the second turn, on the second trial. And also we have to kind of take care of what happened first. So this is a question about two trials of the second player, two plays made by the second player. So again, we start with player number 1 choosing the arrangement A, B, C, D. This is the winner one. And for this one, we're going to say that player number 2 has correctly guessed the pegs in slot number 2 and 3, in the positions 2 and 3. So which play has player 2 made so that the pegs on the positions 2 and 3 are actually the same as the positions 2 and 3 for the player 1? If you check all the answers, only this one is the one that the player 2 could have chosen. So it has our two pegs over there. And again, I'm choosing the second and the third pegs to be the correct ones, but you can choose the first one on the fourth, the first one on the third, and the analysis stays exactly the same. So there's only one possible play that the player 2 made, so that she has two pegs correctly guessed on the first trial. Now, we're wondering what happens on the second trial, second turn. So we can say that on the second turn, the player has to switch position between two pegs. So this is one possible play, choosing to change these two, the third and the fourth. This is another possible play, uh, choosing to change the second and the fourth one. Then choosing to change the middle ones, second and third. Choosing to change the first and the second one. Choosing to change the third one and the first one. We switch positions between these two. And there's another one, of course, the winner option, choosing to change the first and the fourth. So these are all the possible switches between the two pegs that the player 2 can do on the second turn. And only this option would result in all pegs being correctly positioned. So we have 6 possible plays, and only one is the winner. So the probability for this one is simply 1 over 6. And that's it. This is how you analyze the problem without having to know anything about permutations or combinations. Okay?